All right, so one of the reasons we talk about separating hyperplanes or classification using separated hyperplanes is SVM. SVM has gotten a lot of hype in the computer science community lately. And as you'll start to see, figuring out how to use it and when to use it and where to use it is something that's extremely important. Now, it doesn't have the same assumptions that LDA and QDA do. But what you're going to see is a lot of the time it looks like this. You can still use factors. You can still use stuff like that. That's not much of an issue. It's just how that hyperplane then breaks and how it looks is something of great importance. So let's define the mathematical problem, and then we'll talk about what this thing means, because we want to talk about classification using this hyperplane. Let x1 to xn be n p-dimensional observations. So this is your data, okay? And we're going to let x, capital X, be the matrix representation. Each of the n observations are assigned a category for right now. For right now, let's let that be represented by -1 and 1. So it's a classification problem. -1, +1 are the responses, x are your predictors. The goal is to develop a method so that any new data point that shows up, we can have a hyperplane with a rule to classify a -1 and a +1. So let's take a look at the blue and purple dots provided. So see these blues and see these purples. Now there are infinitely many hyperplanes that would cut this space, right? So here's an example of 3, but really anything that put blue on one and purple on the other sets up. If you look at this though, here is another type of hyperplane that would do that. That says anything above and left is blue, anything below and right is purple. Okay, anything that falls on the line, we're just making a random guess. But based on the data we have, nothing falls on the line, right? So let's take a look at what this means. Let's define a hyperplane. Here's the equation for my hyperplane. That if y equals 1, it's greater than 0. And if y equals -1, it's less than 0. So what does that mean? Well, we say something has the separating hyperplane property. It is a separating hyperplane if this statement is true. If for all observations, yi times the equation of the hyperplane is greater than 0. So take a look at this. If y is equal to -1, the equation we're saying is less than 0. So -1 times the equation would be positive, right? Because this is negative and that's -1, right? So -1 times a negative number is positive. If y is equal to 1, we know the equation of the line is greater than 0. So something positive times y, which is equal to 1, is positive, right? So for simplicity, what we're going to do is we're just going to say this hyperplane is f of x, okay? So the idea is for any new observation x star, if x star is positive, we classify it as a 1. If f of x star is negative, we classify it as a -1. The magnitude represents how far away the point is from the hyperplane. The larger the magnitude, the more certain we are of the classification. So something that's really small down here, that's really close to 0, we know is close to the hyperplane. But if it's like -300, what we're going to say is it's far away from the hyperplane, and we're fairly certain of the prediction. But what this does is it shows the closer it is to 0, the smaller the change. So think of it as sort of log odds type, right? The log odds in logistic regression tells you how close the probabilities are to being equal. The closer these metrics are to 0, the closer these measurements are to 0, the closer they are to the hyperplane. So by forcing things towards the hyperplane, or by having numbers that are close to 0, you're able to get a metric of certainty, okay? But we say this hyperplane is a separating hyperplane and has a separating property if this is true. Now, separating hyperplanes cause problems. Think about logistic regression when it fails to converge. A separating hyperplane, which is what logistic regression would be, has major issues, okay? It has major issues. It won't actually give you good estimates if it can find a separating hyperplane, because probabilities get pushed to 0 and 1, and by pushing probabilities close to 0 and 1, Newton-Raphson and those things don't actually converge. So when we're coming up with these ideas, these are concepts you need to be thinking about in the back of your head. But what we're really doing is we're setting up for SVM. And you need to be able to understand and explain the basics of SVM. So that's the reason I want you thinking about hyperplanes and how this works.